This is a video for OCR Pure Core Mathematics, Complex Numbers 5, Complex Roots, 5.1, Solving z to the n equals 1. Solving quadratic equations was covered in a previous video. You should know that these have two roots. They may both be real, as in the diagram at the moment. They may be repeated, and as I bring the curve up towards the axis, they may be repeated, and we get a repeated root here at 1, 0. Or they may both be complex roots. And if they are complex roots, they occur in a conjugate pair. So in this situation, the quadratic does not cut the axis. So we get two complex roots. Two complex roots, a repeated root, two real roots. So if we want to solve the quadratic equation, z squared minus 2z plus 5 equals 0, you can see here by completing the square I get down to two roots for that equation, one plus or minus 2i. Complex roots from a real quadratic equation will always occur in conjugate pairs, and we denote them z and z star. Note that either of the two values could be chosen as z, with the other one being its conjugate. You should also have solved cubic equations to find three roots, some of which may have been complex. And if we look at a cubic like this one, that will have three real roots, whereas one like this will have only one real root, and then we'll have two complex roots, again occurring as a conjugate pair. In fact, every polynomial equation of degree n has exactly n roots. Some of those may be complex, and if they are, they occur in conjugate pairs. Let's have a look at one of the simplest polynomial equations, z squared equals 1. It has two roots, z equals 1 and z equals minus 1. If I show those on an Argand diagram, they'll appear here and here. For z cubed, again showing them on an Argand diagram, I get them here, here and here. And their values are 1 and minus 1 plus or minus root 3i all over 2. Z to the 4 has four roots, plus or minus 1 and plus or minus I, and again on an Argand diagram those four roots are spaced equally around a circle of radius 1. The simple equation z to the n equals 1 has n roots, and one of those roots will always be 1. If n is even, however, there will be another real root at minus 1. All the other roots will be complex numbers which can be shown on an Argand diagram. Let's have a look at this plot here and see what happens as we change the power of n. If I go back to n equals 2, you'll see I get two roots, one at 1 and one at minus 1, 3, 4, 5, 6. I'm always getting a root at 1, and for the even numbers, 6 and 4 and 8, I get another one at minus 1. And then the complex roots appear in conjugate pairs. There's actually a mirror symmetry about the real axis. These two are conjugate pairs, these two are conjugate pairs, and these two are conjugate pairs. Notice that all of the roots lie on a unit circle, and they're evenly spaced by the same angle around that circle. The next video in this sequence is 5.2, the nth roots of unity.